and recap a little bit what we did last time. So last time we talked about energy methods for wave equations. Mostly we talked about sort of separating out for this particular equation, which we solved using WKB, where if you think of a string that has some material properties that determine its response to deformation according to how the deformations accelerate along the string. The damping of the string, say due to friction, and then elastic properties in the string as well. And sort of damping, this is elasticity. And this is sort of derives from Newton's second law. If you had PDE with me, we sort of went through how you get that as a linearization to the full nonlinear wave equation. Okay, and we solved this with the WKB method, right? And that yielded an equation which I could write out in detail, but I'll just write the general form of the solution that we got, which is that you have some slowly varying amplitude. You have some fast phase. Fast varying phase of the wave. And phi of x here is equal to omega theta of x. Okay, and we had taken the case where we assumed that omega is much greater than 1 for some initial condition boundary condition u0t equals cosine omega t, and our domain of our equation is from 0 to infinity. So again, the idea is that you're shaking the string at its left end, and that's causing the propagation of waves whose amplitude is going to slowly vary because of these augmenting material properties of the string, right? You don't have a constant transfer of force into acceleration. You have some damping term, and you have some elasticity term, which can vary in space. Okay, and so we were able to use WKB in order to come up with a solution like that. Okay, and then we also showed, we also showed that the energy and the energy flux, so the change in energy plus the flux of energy, should actually be this whole term here. Okay. So this is like change in energy plus the energy flux is going to be equal to the dissipation. So any change in energy that can't be accounted to by just energy flowing around in the string is the result of dissipation of energy. And if you had a conservative system, you would expect this term to be 0. Okay, but you don't expect this to be conservative because you have a friction term, which is leaking energy out of the system. Okay, and we showed that ext is equal to a half mu squared x dt u squared plus a half dxu squared plus a half beta x u squared. S of xt is equal to minus dt u dxu, and phi of x is equal to alpha of x dtu squared. Okay, and when we studied the energy over some interval, okay, x1 of t to x2 of t, okay, if we assume that x2 minus x1 is small, that the distance between these two phase lines that we're studying is small, okay, then what we found is that in those intervals, we don't expect to see the effects of friction sort of leaking energy out of the system. Okay, so you have to go to higher order in order to see that. Okay, or you have to have a wider interval in order to see the effects of friction. Okay, so so I think that's essentially where we got to. Okay, and we had written down for our WKB solution that E of xt is approximately a half a squared mu squared omega squared plus theta x squared sine squared omega t minus phi. S of xt is approximately omega phi x a squared sine squared omega t minus phi. Okay, and big phi of xt is the leading order alpha omega squared a squared sine squared omega t minus phi. Okay, so averaging over one period, okay, of our forcing oscillation. Okay, so remember that our forcing term, right, is cosine of omega t. So one period would be 2 pi over omega. Okay, so if we average the flux over this, then we have dx. We pull that derivative out of this integral, and we have s of xt dt. And over a single one of these, our energy is going to be periodic, okay? Or our change in energy is going to be periodic, okay? So the over one period, our energy flux is going to be equal to just whatever our energy dissipation is, okay? And so since the average of DTE, okay, over one period vanishes, okay, using that E is like A squared mu squared omega squared plus theta x squared sine of omega t minus phi of x. Okay. So really the only time dependency you have here is just to leading order a sine, which you can integrate and show that it's sorry, it's sine squared here. This will integrate to 0 in this case. Okay. So if we substitute in our other expressions, we have that dx phi x a squared is equal to minus alpha omega a squared, okay? Dx theta x a squared is equal to minus alpha a squared by subbing in our expression for phi sub x, okay? And if we expand this out, we get theta xx a squared plus 2 theta x a ax is equal to minus alpha a squared, or just theta xx a plus 2 theta x ax is equal to minus alpha a. Okay. So this actually implies that A is equal to U0, since the last equation is precisely the transport equation that we get for this wave equation. Theta xx U0 plus 2 theta x dx U0 equals minus alpha U0, okay? And so what we find then is that the transport equation corresponds to the balance of energy over one time period, okay? So you can think of the transport equation then as what tells us how the energy flux and the dissipation are related, okay? This right-hand term here, okay, is the decrease in energy that you get from dissipation. And this left-hand side then is your energy flux, essentially, that you get from the movement of energy along the string. Okay, so in summary, the WKB expansion, okay, helps reveal to us, at least to leading order, these relationships between energy change, energy flux, energy dissipation in the string, okay, and so we can work that out to leading order, but it tells us something in general about the full wave equation as well. And so, of course, you could go from here and go to higher order. You can use these methods on nonlinear wave equations as well, wave equations with alternative sort of modification terms, different kinds of forcing and things like that. You could reintroduce sort of like resonance effects, introduce sort of multiple scales, okay? But for as far as what WKB allows you to do is it allows you to sort of very quickly arrive at the particular form of a wave equation that has you sort of separating out slowly modulated amplitudes, a wave type function, and then some, change to the phase, which would be hard to arrive at simply by using sort of standard perturbation methods. Okay. And you would get sort of wrong answers as well once you tried to compute the energy and other physical properties of the wave. Okay, so that kind of concludes this section, this module on WKB. We are now going to shift over to homogenization theory, and this will kind of be the last kind of main topic of the course before we just get into some research level. A lot of this already is research level, I guess, but some other sort of research extensions of asymptotics. Okay. So what's homogenization? The idea with homogenization is that you have some physical medium or some physical or biological or chemical system, social system that you're modeling, that involves multiple scales. So you may say, well, why isn't this just sort of multiple scale analysis? But the idea in particular is to kind of average out the effects on the smaller scale, but still see the effects of those small scale effects in some sort of homogenized system. Okay, so think about driving a car on a flat road versus driving a car on a bumpy road. Okay, if you apply the same sort of acceleration to the car, it's going to go faster on the flat road than it will on a bumpy road, right? But maybe you're only concerned about how fast on average the car is moving, right? So what you might like to do is sort of average out the effects of all the bumps in the road, okay? And just get some sense for where the car is on average on sort of the macro scale of the system over time. How much those bumps in the system are slowing things down, okay? And so one maybe natural place to start then with homogenization is in systems with diffusion, where maybe you don't have a constant diffusion coefficient, but rather you have a diffusion coefficient that has real variations in its microscale. And you can imagine a number of situations where you might come across this. You may have some porous medium that some chemical is being diffused through, or you may have some porous material that you're heating up, right? And so there may be little air holes in the material, okay? But still the material is managing to conduct that heat, okay? And so you have some material that maybe on average, when you zoom out on the macro scale, it sort of looks like it has kind of a constant material property. But if you zoom in and look at a micro scale, there's these little variations, okay, that you care about, but maybe you don't want to have to know every single thing about the solution that emerges from that micro scale, okay? So the idea with homogenization is to, kind of, homogenize over those micro scales and get you homogenized equation and homogenized properties of materials, okay? So we're going to start with an introductory example, and we're going to consider the following boundary value problem. Okay, so we're not even going to sort of deal with time-dependent problems. We're going to deal with a one-dimensional, kind of elliptic problem, okay? The steady state diffusion equation, okay, with some forcing, right? And so if D is constant here, this is a pretty standard second order differential equation that you could surely just integrate in order to get the solution here, okay? So we'll take, say X is just the unit interval, and we have some boundary conditions. U of 0 equals A, and U of 1 equals B. Okay, and so you could think of this as, you know, having some bar, okay, that you're heating at both ends, okay, and that has some heat conduction properties, okay, and that you're also applying some, you know, heat to throughout the bar. And the question is, if D is not just constant, but if it has some, you know, microstructure, and it could also have some macrostructure as well, okay, can we get a good approximation for what the steady state temperature is of that bar, okay? And this doesn't just apply to heat equations. There's other equations, surely, for which this is a steady state solution. So in general, we're going to call D a conductivity tensor. It just tells us something about the conductive properties of our material, okay? And we're interested in the particular case where D is the following function. I'm going to write the function like this. It's some function of x, and it's also some function of x divided by epsilon, which would be the microscale. So as you change x just a little bit, okay, this variable is going to change a lot because epsilon is small, okay? So I know we're not in time, but you have, you know, sort of slow and fast, okay, variation, okay? In other words, macro and micro scale variations in this case, okay? So let's take something concrete, which we'll come back to later, okay? Let's say D of xy, okay, where we'll assign y to be this microscale now, sort of treating it like another variable, like method of multiple scales. Let's say that this was something like 1 over 1 plus alpha x plus beta g of x cosine of y, okay? So in this case, right, if we just average over this, right, we would just have 1 over 1 plus alpha x, okay? And we would just have some inversely linearly varying function here. So alpha equals 0.1, beta equals 0.1, epsilon, I think I need an epsilon out in front of somewhere. Oh yeah, or epsilon is just our scale of this microstructure. And let's say g of x equals e to the 4x x minus 1. Okay. So d then, as we vary x, right, it's going to be some decreasing function with this sort of microstructure in it. Okay. All right. So what's the goal here? Our goal in general is to replace d of xy, okay, in our boundary value problem with some averaged coefficient d bar of x, okay? And we want it to be independent of epsilon, okay? Now, there's a few ways we could do this, right? You could say, well, maybe I'll just average D up front, plug that average quantity in, and try and approximate my differential equation that way. Okay. So naively, what you could do is average over the microscale and say, I'm going to say that D infinity, this is going to be my averaged diffusion, is going to be the limit as y goes to infinity of 1 over y, the integral from 0 to y d of xr dr. Okay, so treat this y like a, a separate variable, okay, and just take the average over that, okay. And for our example above, okay, this would come out to be 1 over the square root of 1 plus alpha x squared minus beta g of x, whole thing squared, okay? And we would just take this and plug it back in here, okay? So if we tried this, okay, this could be a bad approximation, okay? Of course, if the solution to star with d infinity does not approximate the full solution well, okay? And in general, this is possible, okay? Now, I'm not going to say that that approach is always bad, okay? Sometimes it ends up working well, okay? And if you want to try something quick, okay, you can often do that. And oftentimes when you're measuring some physical system that has some, continuum properties, maybe you just don't get a good enough measurement. And so that's what you end up using anyway for your model system, okay? So it's not necessarily always bad, but you can carry in some more precision if you use sort of the logic of method of multiple scales to more systematically boil down this equation, okay? And if you think about it, like, sort of what we learned from method of multiple scales, right, is if some function is sort of tucked, within a differential operator or something like that, you maybe wouldn't expect that just because you, do some averaging and replace that function with another function, that's going to give you a good approximation to your original system, okay? So as an alternative, you can try the method of multiple scales, okay? And you say, well, didn't we already go through all this? Okay, but we're gonna get some different features of method of multiple scales when we use it on a homogenization type problem. In particular, we have to go all the way up to order epsilon squared in order to kind of see the resultant equation that we get by applying this approach. We can't just stop at order epsilon in this case, okay? And the other thing is that rather than introducing an additional multiple scale, right, like we did for our time-dependent problems, what we're trying to do here is actually eliminate a fast scale, okay? So if you remember, like our whatever Mathieu equation, all these forced oscillators that we derive sort of amplitude equations for, okay, that's not the result that we want to try and get by applying method of multiple scales here. We want to get rid of actually the one of the multiple scales, okay? And we're going to do that by enforcing boundedness. So the principle is somewhat similar to these, kind of secular equations that we got before. It's really sort of forcing a bounded solution to our multiple scales problem. And those conditions will end up being equations that will tell us something about our leading order behavior of our system. Okay, so we have to make some assumptions, right? So we assume that d of xy is going to be smooth, okay? And we're going to bound it by some function. So that one function will be called d little m of x, and that's going to be less than or equal to dx of y. And then it's going to be upper bounded by d big M of x. And that this is true for all x that live in 0 to 1 and y greater than 0. Okay. So what this should tell us is that we're going to run into issues that maybe we could deal with by some other means if our diffusion goes all the way down to 0. Okay. And we're also going to run into issues if our diffusion diverges to infinity at some point. Okay. But of course, you would expect that. So we're just saying that we can define some functions that will upper and lower bound the effects of the microscale on the diffusion. Okay. And that dm and d big M are continuous. Okay. So one's lower, one's uppercase there. Okay. All right. So as is typical with method of multiple scales, right? We want to take this derivative and we treat it as a total derivative. And it's going to be 1 over epsilon d sub y plus d sub x. Okay. So what do we get for our new equation? Star is going to become dy plus epsilon dx dxy times partial with respect to y epsilon dx u. Okay, and then I had to multiply through by 2 epsilons in order to get rid of those sort of 1 over epsilons up front. Okay. Now, as you might imagine with method of multiple scales, we also need to expand our actual solution, and we'll just try a regular perturbation expansion to start with. Okay, so we'll assume that u is approximated by u0 of xy plus epsilon u1 of xy plus epsilon squared u2 of xy, so on up the chain there. Okay. And that u0, 1, and 2 are smooth and bounded and all of that. Okay. So if we look at order 1 then, okay, I can pick off those terms. So I have a dy here, and the d here. Okay, I'll get a u0 there. And then there's nothing on the right-hand side. So I just have a nice homogeneous equation at order 1. Okay. And our general solution is going to be u0 xy is equal to c1 of x plus c0 of x times the integral from y0 up to y ds over d of xs. Okay. And y0 is just some constant that's fixed but arbitrary. Okay. Now, what's the problem here? Well, because y is our microscale, right? Y could, like, blow up. And remember that this is always bounded away from infinity. Okay. So as we continue to take y out to infinity, okay, this integral is just going to contribute more and more and more. Okay. So the only way to ensure a bounded solution is to just say, well, c0 of x, which is arbitrary to this point, needs to be 0. I need to eliminate this term to have a bounded solution. Okay. So for u0 to be bounded, okay, we're going to take c0 is equivalent to 0. Okay, since the integral is unbounded as y goes to positive infinity. Okay, right. So that is if y is greater than y0, then we have that the integral y0 up to y of ds over d m of x puts a lower bound on this integral. Okay, ds over dxs, and y minus y0 over dm of x is less than or equal to the integral of y0 up to y ds over dx of s. Okay, so right, so the left-hand side goes to infinity as y goes to infinity. So right-hand side does too. Okay, therefore, we're going to take u0 to just be some function of x, right? And it'll just be c1 of x. Okay, and note that y minus y0 over dm of x is lower bounding ds dx of s, and it's upper bounded by y minus y0 d little m of x. Okay, and so that integral is unbounded, okay, but the growth is what? What can we say about the scaling of the growth of this integral here? Asymptotically. As y gets big, this integral is a function of y. Does it scale non-linearly or linearly?
Linearly.
Yeah. So it's lower bounded by a linear function and it's upper bounded by a linear function. Okay. So it must have some, linear growth rate. Okay. All right. So that, which may be useful later. Okay. If that shows up again. All right. So let's go to order epsilon. So let me look back at this equation now. I have an epsilon here. Okay. I have an epsilon here that'll pair up with that derivative. Still, I have no right-hand side. And then I'm going to have a u0, right, that's going to pair up with those epsilons. And then this operator is just going to act on my u1. Okay. So what I get at order epsilon is I get dy, dxy, dy u1 is equal to minus dx u0 times dy d. Okay, and if we integrate with respect to y twice and use that u0 is just a function of x, then we'll have the following: dxy dy u1 is equal to b0 of x minus dx u0 dxy. And this implies that dy u1 is equal to b0 of x over dxy minus dx u0. Okay. And I can integrate this and I'll get some expression for u1, which I'll write on the next page. Okay. So u1 of xy is equal to b1 of x plus b0 of x, integral from y0 up to y, ds over dxs minus y dx u0. Okay, so here's this integral again. Okay, which is why it was good to, to sort of make a note about the scaling law of that integral. Okay, so So what's the problem over here? Well, again, I got to worry about stuff that's going to blow up as y gets large, because y is the micro scale, and so y can be large, okay, in this case. And so my last two terms on my right-hand side, okay, as we said, they're going to increase linearly with y, okay, for y getting large, okay? So as a result, let's require these terms to cancel, okay? And that means that in the limit as y goes to infinity, 1 over y, b0 of x, integral from y0 up to y, ds over dxs minus y dx u0. I want that to just be equal to 0, okay? Now I can rewrite this a bit, okay, as dx u0 is equal to this thing that I'll define as d to the minus 1 and this this sort of infinity norm here, b0 of x, where this expression is equal to the limit as y goes to infinity of 1 over y, integral from y0 up to y, ds over dx of s, okay? And I'm going to call this expression here dagger, okay? Now, this looks a little bit different from what I was doing at the beginning, my naive approximation, okay? So this gives us a little bit of a clue of what gets revealed by going through this method of multiple scales approach. Rather than just taking a straight average by integrating over, it seems like the thing to do is to average the inverse and then take the inverse of that in order to get my effective diffusion coefficient, okay? Now that's still taking a mean, but it's a special kind of mean called the harmonic mean, okay? And so by just following our nose with this approach, we found that that's the more correct way to average this diffusion coefficient in this case. And this integral is going to sort of continue to show up as we go up to higher order, okay? And I think I only have 2 minutes left, so I won't rush through what's next. But the idea of how to wrap this up is that we need to proceed to order epsilon squared now in order to determine u0. We already have this expression that's something like the start of our average diffusion coefficient. That's going to enter into our order epsilon squared equation. And then we'll have an equation for u0 that we could presumably solve in order to find out what the leading order behavior is for the homogenized equation, okay? So that's what we'll finish up with on Monday, and then we'll move on to two-dimensional but still sort of elliptic problems. And then the next step after that is traveling waves and sort of bistable type equations, okay? All right, so any question about this approach that we've done so far? Okay.
Is this notation with the brackets supposed to be reminiscent of some other notation that just like is, I guess I look at this and I see it looks like a functional, but I'm wondering if there's maybe more connections or more motivation for the notation that would connect it to topics I've already seen.
Yeah, I mean, it's sort of like it's sort of like a norm, right? Because you know this is positive, and you're taking this function and you're integrating it, and you know, dividing um, by the domain that you're averaging over. So it's like an average, okay, but it's only over one dimension of your function, in this case. And so so in that sense, it's not quite um, like a norm, right? But it's sort of like a running average, essentially, over one of the dimensions of your function that you have in this case.
It looks like an expectation value. Is that where the notation comes from?
Yeah, yeah. Okay. All right. So I'll see you on Monday then. Have a good weekend.
Thanks, Zach.